Hello. In this video I'm going to be explaining and going through this problem here. So I'll first read it out to you. Two boats, A and B, move away from a buoy anchored at the middle of a river along the mutually perpendicular straight lines. Boat A moves along the river and boat B moves across the river. Having moved off an equal distance from the buoy, the boats then returned. Find the ratio of times of motion of boats, tau A over tau B. And here tau A is the time taken by boat A to complete the whole journey, and tau B is the time taken by boat B to complete the whole journey. So the question is asking us to find the ratio of these two times if the velocity of each boat with respect to water is eta, so that's a Greek letter eta, which equals 1.2. So find the ratio of the times of motion of the boats if the velocity of each boat with respect to water is eta times greater than the stream velocity. And when the question says stream velocity, it means the velocity of the water flowing in the river. Okay, so I'm first going to draw out a diagram to represent this problem so we can understand it better. Okay, so I'll first draw the river. So here's one bank of the river and another bank of the river. And we know that there is a buoy anchored at the middle of the river, so I'll just draw that. There's the buoy, and I'm just going to draw on the stream in a blue pen here. And the question didn't tell us in which direction the stream velocity is, so we can choose. So I'm going to choose the stream velocity to be in this direction. And the question tells us that we have two boats which are moving along mutually perpendicular straight lines, where boat A is moving along the river and boat B is moving across the river. So we can see that boat A is going to be moving something like this. So it's going to start off at the buoy and it's going to move a certain distance along the river and then it's going to return like this. So that's its forward journey and that's its backwards journey. So this is for boat A, and similarly boat B is going to move across the river. So again, it's going to start off at the buoy and it's going to move a certain distance and then it's going to return. So that's forward journey and it's reverse journey. And that's for boat B. And the question also tells us that the distance moved off by each boat is equal. So we can call that distance x. So on our diagram, so distance between there and there, that is x. And also the distance between here and here, that is also x. So equal distances. And a really key part of this question is that it tells us the velocity of each boat with respect to water is eta times greater than the stream velocity. So the important bit is the with respect to water, because here water, the word water implies that these velocities are with respect to a stationary observer, so something that's not moving. So in this case we could say that that stationary observer is on top of our buoy in the middle, so I'm just going to put a cross in the buoy to show that that's where our observer is. And this diagram that I've drawn here, it's from the frame of reference of this stationary observer. So this observer sees that the two boats A and B, they move off along these mutually perpendicular straight lines, and these two paths of A and B, these are the resultant paths. So the way that we can go forward with this question is we need to calculate tau A and tau B. So if we start off with tau A, we can see that the time taken by boat A to complete this journey is going to be the time taken for it to go first upstream, because remember our stream velocity is in that direction. So the time taken for boat A to go upstream, and then the time taken for it to return. So the way we work out the time, so if I write tau A, that's going to equal, so the distance that it travelled, so x over its velocity when it was travelling upstream, so I'm going to call that v upstream, plus x over its velocity when it was travelling downstream, so v downstream. And these two velocities, these are velocity magnitudes, and they are the resultant velocities. And similarly for tau B, in this case it's not going to be upstream and downstream, because boat B, it's not travelling upstream or downstream, it's going across the river. So for tau B it's going to be x over v, I'll call it v forward, so for its forward journey, plus x over v return, so boat B's return journey. So if you can calculate these four velocity magnitudes, then that's how we're going to solve this question. But the most important thing to remember is that these paths shown here, they are the resultant paths from the frame of reference of this stationary observer here, which is on our buoy. So that's the most important part of the question. And another thing to bear in mind is the question tells us that the velocity of each boat with respect to water is eta times greater than the stream velocity, so that tells us the velocity magnitudes of the two boats with respect to water are equal. So if I call the velocity of boat A as VA, and the velocity of boat B VB, we know that they are equal, so I'm just going to call that a different velocity, just V, just to make things more simple. And we're going to be using that in the rest of the question. And remember, these velocities are with respect to the observer, the stationary observer on the buoy here. Okay, so I am going to start off with boat A. So I'll draw the river again and the buoy. So we have the stream, and boat A is moving away from the buoy. So I'll say in this direction, and the stream is moving in the opposite direction. So I have taken this direction as positive, so if the velocity of boat A is VA, then this vector, this velocity vector, is just VA, positive VA. And the stream velocity, because it is going in the opposite direction to the boat, I have to call that negative VS. So the negative sign indicates that it is in the opposite direction to the boat. So what we have to calculate now, the reason I'm drawing this diagram, is that I want to work out the resultant velocity for boat A. So to work out the resultant velocity, I have to add these two vectors together. So you get VA plus minus VS, or just
VA minus VS. That is the resultant velocity for when boat A is moving upstream. So to work out the times, we have to work out the magnitude of this resultant velocity. So the magnitude of VA minus VS, that is equal to V minus VS. So that is the magnitude of boat A's velocity when it is moving upstream. This is all from the frame of reference of our stationary observer. So if I now do it for when boat A is moving downstream, this is the buoy. We have the stream here. This time boat A is moving towards the buoy, and it's no longer, the boat's velocity is no longer VA, it is negative VA because it is moving in the direction opposite to what it was before, and the stream velocity is still negative VS. Once again we have to work out the resultant velocity, so that is minus VA minus VS, and the magnitude of this is simply just V plus VS. So now I have the two resultant velocities, the magnitude of the two resultant velocities. I can work out what tau A is, the time taken by boat B to complete this whole journey. So tau A, that time, is equal to the distance it travels, x, over its velocity, which was V minus Vs, plus, for the downstream journey, x over V plus Vs, which upon simplifying gives 2Vx over V squared minus Vs squared. So we have worked out how long it takes for boat A to complete that journey upstream and downstream.
Okay, so now we need to do something similar for boat B. We need to work out how long it takes boat B to complete its whole journey. So for boat B, so if I draw a diagram with the river again, so here's the river, and there's the buoy, and here is the stream, and the stream velocity is still in this direction, there. Okay. But for boat B, the important thing to remember is that it is travelling across the river, and this is from the frame of reference of our stationary observer on the buoy. So this path of boat B is the resultant path. So we know that boat B's resultant velocity vector is going to be this. But that means boat B must have been going with such a velocity so that the resultant between that velocity and the stream velocity gave this green velocity vector here. So let me just label minus Vs there. So we can see from our vector diagram that boat B's velocity vector, it would have to be this vector here. And we can see that this vector so minus vs plus this vector, which is going to be vb. So you can see minus vs plus vb gives this resultant vector, which is what we want because our stationary external observer sees that boat B is travelling perpendicular to the stream velocity, like that. And this resultant vector here, that is equal to vb minus vs. And like we did for boat A, we want to work out the magnitude of this. So we want to work out the magnitude of this because the external observer, the two parameters that the external observer is seeing is the distance x that boat B travels and the time tau b that boat B takes to make this journey. So we need to work out the magnitude of this velocity vector, and we can do that using Pythagoras because we have a right angle triangle here. So the real advantage of drawing it out like this is because we can see the right angle triangle really clearly. So we can see that the magnitude of this resultant vector here, so the magnitude of vb minus vs is equal to, remember our vb is equal to v, so its magnitude is equal to the magnitude of va, which is equal to our v. So this is simply equal to the square root of v squared minus vs squared. And so this is the velocity of boat B as it was moving away from the buoy, so it's v forward, this velocity here. So a common mistake when doing this would be to assume that boat B's velocity, so vb, is this perpendicular velocity here, but that's not right because this perpendicular velocity is what our stationary observer sees. That's the resultant, so you can't assume that vb is this. So this is what actually happens. Boat B goes at an angle in order for it to travel along the mutually perpendicular straight line going across the river. Okay, so we can do something similar for when boat B is returning to the buoy. So if I draw the river again, there's the buoy, and the stream velocity, I'm going to draw it here this time, so that's minus vs, and this time boat B is returning to the buoy, so again its resultant velocity is going to be perpendicular to the stream velocity, so it's going to be like this. It's going to be like this. So perpendicular, and again we need to work out what vector boat B has to move along so that the resultant is this vector. So we can see it's going to have to be this vector because this vector plus minus vs gives this green vector here, and again I'm going to label that our VB. Now just note that this VB, it's not actually the same as this VB because they're different vectors, they have different directions, but they do have the same magnitude, so that's why I'm calling them both VB. So our resultant vector here is again VB minus VS, and again the magnitude, which we need, the magnitude of this vector, it's the same as what it was before. It's the square root of v squared minus vs squared. So notice how the velocity of boat B, it was the same when it was travelling away from the buoy and when it was returning to the buoy. It was the same velocity. So we can now work out what tau b is. So tau b is equal to, so the distance boat we travelled, so x over its velocity when it was on the way, so v squared minus vs squared, plus when it was returning, x over square root of v squared minus vs squared, so there's the same thing. So in total that is equal to 2x over square root of v squared minus vs squared.
Okay, so the very final part of the question is working out that ratio of time of motion, tau A over tau B. So now we know what tau A equals and what tau B equals. It's fairly straightforward. So tau A over tau B, that is equal to 2vx. So yeah, so you can see what tau A is there. Tau A is so tau A over tau B, that is 2vx over v squared minus vs squared multiplied by the square root of v squared minus vs squared over 2x, which after you simplify gives you v over the square root of v squared minus vs squared. Now in the question it tells us that v over vs is equal to eta. So if you divide every term in this expression by vs, then you get v over vs in the numerator, and in the denominator you get v over vs squared minus 1, which equals eta over the square root of eta squared minus 1. And that is the final answer.